everyone, and welcome to Lecture 14. We're talking about basic functions again, graphing basic functions. But here we're going to be talking about variations of basic functions. And the first thing that we're going to talk about are vertical variations. Everything that we do in this section will affect the graph's appearance vertically, but not horizontally. And the first thing that we can do is take a graph, y equals f of x, and given some constant c greater than 0, multiply f of x by c. For example, here we have y equals f of x. Here we have the graph y equals c times f of x. We've taken the y coordinate, f of x, and multiplied it by c. And when we do that, when we multiply f of x by c, this stretches the graph vertically by a factor of c. Let's look at a familiar graph. We'll let this be our f of x. And notice that we use our x values -1, 0, and +1 to create a skeleton to hang this graph on. When x is -1, y is 1. When x is 0, y is 0. When x is 1, y is 1. And we look at this and we say, oh, I know what this is. This is the graph of f of x equals x squared. And you're probably right. What happens if we multiply the y coordinate by c? Y equals cf of x. We use the same x values, -1, 0, and +1, to form our skeleton to hang this graph on. But now, the y coordinate when x is -1 isn't 1 anymore, it's c. The y coordinate has increased in value by a factor of c. Or another way of saying that, we took the y coordinate of the old graph and multiplied it by c. And when x is 0, we take the y coordinate of the old graph, which is 0, and multiply it by c. C times 0 is still 0, so this point isn't changed. Then we look at the point where x is 1, and we multiply the y coordinate by c. C times 1 is c. So these are the points on the new graph that form our skeleton. And notice what we've accomplished here. By taking the y coordinate f of x and multiplying it by c, we've stretched everything out vertically by a factor of c. We've taken this point where the y coordinate was 1, and we've stretched it upwards so that now the y coordinate is c. We took the y coordinate at this point, which was 1, and we took that point and we stretched it upward vertically so that its new value is c. Now let's apply this to all of the basic functions that we've been working with. Our first real example, f of x equals x squared. We use our old friends -1, 0, and +1. X values that we can use to compute y values on the graph. When x is -1, -1 squared is +1. When x is 0, 0 squared is 0. When x is 1, 1 squared is +1. That yields 3 points on the graph that we use as our skeleton to hang the rest of the graph on. And what we're going to do is we're going to take this function, f of x equals x squared, and we're going to multiply the y coordinate, x squared, by some positive constant c. And there are two ways that we can do this. Let's do it both ways. We can take our three friends, -1, 0, and +1, and take each of these and plug them into the function f of x. When x is -1, f of -1 is c times -1 squared. See, -1 squared is +1, so this is just c times 1. There's our y coordinate. When x is 0, we take 0 and put it in for x, and we have c times 0 squared, which is 0. That gives us this point. And when x is 1, we take x equal 1 and plug it in for x, and we get c times 1 squared is c. That gives us the y coordinate when x is 1. And this is what our graph looks like. Now, we didn't have to do it this way. We could have said, you know what? Multiplying x squared by c just takes this graph and stretches it vertically by a factor of c. So if x is 1 here, it's going to be c here. If y is 1 here, then y is going to be c times 1 here. If y is 0 here, then y is going to be c times 0, or 0 here. If y is 1 here, then y is going to be c times 1 here. We took all of the y coordinates and multiplied them by c. This becomes c times 1, which is c. This becomes 0 times c, which is c. This becomes 1 times c, which is c. Let's do one more example and then work with some real constants. Another basic function, f of x equals x cubed. Remember, to graph this function, we used our old friends, x equal -1, x equals 0, x equal +1. And we took each x value, plugged it into the function, and got the corresponding y values. At least hypothetically, we know what the graph of this function looks like. Now, what happens if we vary this function a little bit by multiplying the y coordinate, x cubed, by some positive constant c? Well, in that case, the y coordinate of this point is multiplied by c. The y coordinate of this point, which is 0, the y coordinate of this point is multiplied by c, but 0 times c is still going to be 0. And the y coordinate of this point, -1, is multiplied by c, so we get -c. And this graph has been stretched out vertically by a factor of c. Horizontally, the graph hasn't changed, but vertically, we took the graph where the y coordinates were +1 and -1 and just stretched them out so that the new y coordinates were c and -c. Okay, let's use some real numbers. Here's a good one to start off with. F of x equals 5x squared. And for reference, we go back to the related function, f of x equals x squared. And we look at the key points on this graph. For each of the key points, we're going to take the y coordinate and multiply by 5. So instead of this y coordinate being 1, it's going to be 5. We'll look at this key point. We're going to take the y-coordinate and multiply by 5. But 5 times 0 is still 0, so this is actually a point on the new graph as well. And we look at this point where x is 1, and the y value at this point is 1 on the original graph. To get the point on the new graph, we're going to multiply that by 5. So when x is 1, y is 5. And just like that, we have the new graph. Well, that wasn't too bad. Let's do another one. Let's try a variation of another basic function, f of x equals x cubed. But remember what the graph of this function looks like. And in case we just blank out for a minute, just remember our 3 friends. X equal -1, x equals 0, x equal +1. When x is -1, -1 cubed is also -1. When x is 0, 0 cubed is 0. And when x is 1, 1 cubed is 1. So that gives us our 3 points on the graph that we can use as a skeleton, and we hang the rest of the graph on that. Well, now we have a variation of the original function. We take x cubed and we multiply it by the constant 4, and that's going to stretch everything vertically by a factor of 4. Let's see how that turns out looking. Pat Rossi, the guy who couldn't draw straight. Here's our 3 friends again. -1, 0, and 1. And first of all, remember that with this kind of an alteration, we're just multiplying by a positive constant. With this kind of a variation or an alteration, the shape of the graph is not going to change, just the vertical scale. So the graph is still going to look like this. Now we plot some points. Or better still, we realize that the corresponding points on this graph have y-coordinates that are 4 times the values of the y-coordinates on the original graph. The y-coordinate here is -1, so the y-coordinate here is -4. The y-coordinate here is 0, so the y-coordinate here is going to be 4 times 0, which is 0. The y-coordinate here is 1. So the y-coordinate here is going to be 4 times 1, or 4. Okay, we got 4 times x cubed. Let's pull this kind of stunt with some of the other basic functions that we watched in the previous video. And let's try a variation on the graph of f of x equals x squared. This is one of the basic functions whose graph we're memorizing. And this one's kind of peculiar because its graph does not extend to the left of the y-axis. This entire graph starts at the y-axis and goes to the right, but there's no portion of this graph that extends to the left of the y-axis. And I'm going to modify this let's try a positive constant less than 1 for a change. And we want to graph this function. The graph of this function is going to have the same shape as the graph of the original. It's just that vertically the scale is going to be altered, that's all. So let's find this point. We're taking f of x and we're multiplying the y coordinate by 1/2. Here the y coordinate is 0. So over here the y coordinate is 1/2 times 0, which is 0. Here the y coordinate is 1. So over here the y coordinate is going to be 1/2 the y coordinate here. So the y coordinate will be 1/2. This is going rather smoothly. Let's do one more. Another of our basic functions, the cube root of x, and we remember what its graph looks like. If we black out and forget for a second, just remember our three friends, x equal -1, x equals 0, x equal +1. We can use those x values to plot points on the graph. And this is what the graph ends up looking like. Okay, let's do a variation on this graph. F of x equals 2 times the cube root of x. Well, by now we ought to know the drill. If we take the y value of the original function and multiply it by a constant, the shape of the graph doesn't change, just the vertical scale. This constant is going to multiply everything vertically by a factor of 2. It's going to take this graph and stretch everything vertically by a factor of 2. The shape stays the same, just the vertical scale changes. And to get this graph from the original, that we just take the y coordinates of every point on the original and we multiply them by this number. The y coordinate here is -1. So on this graph, we multiply it by 2. The y coordinate here is -2. The y coordinate of this point is 0. So the y coordinate of this point is going to be 2 times 0. The y coordinate of this point is 1. So the y coordinate of the corresponding part, the y coordinate of the corresponding point is going to be 2 times 1. I think we're getting the hang of this. And I'm never one to leave well enough alone, so let's try something else that we can do to alter the graph of a function vertically. A new variation. We're going to take the original function f of x and multiply it by -1. So given the graph of a basic function y equals f of x, we want to be able to graph the function y equals negative f of x. And I'll tell you exactly what happens here. Multiplying the y value of a function by -1 takes the entire graph and revolves it about the x-axis. So going from here to here, we're going to take the graph of the original function and we're going to revolve it about the y-axis. Whoops. Well, I'll draw these points. This is what the original function looks like. What I have in red on the board is the original function. But when I take the original function and multiply the y coordinate by -1, that's going to rotate that graph about the x-axis. So this part is going to be revolved or rotated about the x-axis so that it comes down here. And this part is going to be rotated about the x-axis or revolved about the x-axis so that this point comes down here. Crud. And there we have the graph of the new function. Multiplying a function by -1 just takes the original function and revolves or rotates it about the x-axis. Well, that was so much fun, I want to do it with another function. Let's look at our basic function, y equals x cubed, and we're going to vary it. We're going to take the y coordinate, x cubed, and we're going to multiply it by -1. What is that going to do to the original graph, the graph of the original function? If you said it's going to revolve it or rotate it about the x-axis, you're right. So let's see what the original graph looked like. This is what the original graph looked like. This part that's below the x-axis is going to be revolved above the x-axis like this. And this part that's above the x-axis is going to be revolved below the x-axis, like this. Voila! This is what the graph of y equals negative x cubed looks like. We just took the original graph, both sides, on both sides of the y-axis, and flipped them over the x-axis. We revolved the original graph about the x-axis. Let's do one more like this before we start putting some things together. We haven't worked with this basic function today, so let's work with it. The graph of y equals absolute value of x. This is one of those that we're supposed to know. And if we blank out and forget what this looks like, we can go to our three friends, -1, 0, and 1. The absolute value of -1 is +1. The absolute value of 0 is 0. The absolute value of 1 is +1. So that gives us our 3 points on the graph to form the skeleton on which we hang the rest of the graph of the function. Well, we multiply the y value, absolute value of x, by -1. And I think we know by now that that's going to revolve the function about the x-axis. Now, this is what the original function looks like. This is the original function. But we're going to take this thing and just revolve it about the x-axis. And that's going to give us the graph of that function. And visually, did we get this function by taking this graph and revolving it about the x-axis? We sure did. And notice something, the x-coordinates of our key points don't change. X equal -1, x equal -1, x equals 0, x equal +1, x equal +1. The x-coordinates don't change. What happened to the y-coordinates? Well, this y-coordinate is multiplied by -1. This y-coordinate is multiplied by -1. And this y-coordinate, which is 0, yep, it's multiplied by -1 as well, and it remains equal to 0. So the x-coordinates remain the same when we multiply by -1. The y-coordinates are multiplied by -1 just like we expect. Okay, now let's start combining these tricks. Let's look at this. Y equals -3x squared. It's telling us to graph it. And even if I'm doing this just for myself, here's how I'm going to approach it. I'm going to draw the graph of the basic function that this is related to. What do you think that would be? Y equals x squared, right? So I'm going to take the graph of y equals x squared, and I'm going to draw that graph. There, that's the graph of y equals x squared. Now what I'm going to do is I'm going to take this graph and I'm going to get the graph of y equals 3x squared. And what happens here? Isn't it true that I just stretched this graph out vertically by a factor of 3? So that instead of the y coordinates being 1 here and here, the y coordinates are going to be 3. Okay, now I've got y equals 3x squared. The next thing I'm going to do is I'm going to take y equals 3x squared and multiply it by negative 1. And by the way, I guess maybe what we really want to be doing this for is f of x. We haven't done anything wrong here because as far as we're concerned, y and f of x are one and the same thing. But I think in our book they're going to be using f of x a lot more than y. So let me replace y with f of x. Now, how do I get the graph of this function? Don't I just take the graph of f of x equals 3x squared and rotate it about the x-axis? So let's see, the point 0, 0 right here will stay put. The point 1, 3 gets rotated about the x-axis, so it's going to be negative 1, negative 3. And this point, 1, positive 3, is going to be rotated about the x-axis. It's going to become 1, negative 3. And this is what the graph of our function is going to look like. That wasn't half bad. Let's do another one. And by the way, I mean it when I say that if I have to graph this function, probably what I'm going to do is I'm going to graph x squared first. And from this, I'm going to graph 3x squared. And from this, I'm going to get the graph of negative 3x squared by taking this thing and flipping it about the x-axis. And you know what? It didn't take me long to draw these three graphs. And doing it this way, I can reason everything out. Graph f of x equals negative 2x cubed. Now, how am I going to do that? Probably the best way for me to do that is to draw the graph of the basic function in my repertoire of functions that most closely resembles this, and that's going to be f of x equals x cubed. I'm going to draw the graph of f of x equals x cubed. And we remember the three key points that we use to draw this thing. Voila! The graph of f of x equals x cubed. Next, I'm going to draw the graph of f of x equals 2x cubed. And multiplying by 2 just stretches the original graph out vertically. Maybe I should make this a little bit more pronounced. We have a y-coordinate of -1 here. We're going to multiply that by 2, so the y-coordinate is going to be -2. We have a y-coordinate of 1 here. We're going to multiply that by 2, so the y-coordinate is +2. And the y-coordinate of this thing is 0. Any point on the origin doesn't move when we multiply a function by a constant. So here's the second graph in our series of steps. And we only have one more to graph. To get the graph of this function, we take f of x equals 2x cubed, multiply it by -1. Okay, we're about to arrive in the promised land here. Now, when we take this graph and multiply it by -1, what does that do to this graph? When we multiply a graph by -1, doesn't it flip that whole thing about the y-axis? So this part is going to be revolved about the y-axis. And this part's going to come up here like that. This part is going to be revolved about the y-axis. It's going to come down here like that. And this is what our graph looks like. Ah, that wasn't hard at all. Now there's one more vertical alteration that we can make, and we're going to do it now. This is the third and final thing that we can do to alter a graph's appearance vertically. When we take the graph y equals f of x and we add c to the y-coordinate, that shifts the graph of y equals f of x vertically by c units. So let's give a basic example. Let's consider the graph f of x equals x squared plus c. What are we doing? We're taking f of x equals x squared. And remember, f of x is just another name for y. So we're taking the y-coordinate of the graph of x squared and we're adding c to that y coordinate. So we take our graph, f of x equals x squared, and to get the graph of the function f of x equals x squared plus c, remember what we're doing here. We're taking c and we're adding it to the y coordinate of every point on that graph. So let's see, this point is negative 1, 1. This point is 0, 0. This point is 1, 1. Well, if I add c to the y coordinate of this graph, that's going to make the y coordinate equal to c. The x coordinate will stay the same, but the y coordinate is c. If I add c to the y coordinate of this graph, then the y coordinate of that graph is going to be 1 plus c. And if I add c to the y coordinate of this graph, the y coordinate is going to be 1 plus c. Now, what happened when I took the graph of this function and I added c to the y coordinate? Didn't I just take the original function and grab the graph and move the entire graph up c units? This point moved from 0, 0 to 0, c. This point moved from 1, 1 to 1, 1 plus c. Yeah, that's what happened. I just took the original graph, this thing, grabbed a hold of it, picked it up, and moved it c units higher. That's what's going to happen every time we take the graph of a function and we add a constant c to it. Let's do a couple more examples. We want to graph the function f of x equals x cubed plus 1. So to start off with, we look at the graph of the related function x cubed just for reference. And then based on what this graph looks like, we're going to draw the graph of f of x equals x cubed plus 1. And what we're going to do shift up or shift vertically 1 unit in the positive direction. Oh, crud. I meant what I said, I just didn't do what I said I was going to do. I'm going to take this whole graph and just move it up 1 unit. So this point is going to get moved up 1 unit. X will stay the same, but y becomes 1. So this is going to be a point on the graph. X equals 0, y equals 1. I'm going to take this point and move it up 1. X is going to remain at negative 1. but I'm going to add 1 to the y coordinate. This is -1 right here. I'm moving up 1 unit, and y is going to be 0. So this is going to be a point on the new graph. And this point, I'm moving this point up vertically 1 unit. X will stay the same, but since I'm going up 1 unit, I have to add 1 to the y coordinate. Voila. And notice that essentially the shape of the graph stays the same. Not bad, huh? Let's do one more. Graph f of x equals absolute value of x minus 1. Now to do this, we start off with one of the graphs in our repertoire of basic functions. The graph of the function that most closely resembles this, and that's going to be the graph of f of x equals absolute value of x. We're going to use this as our model. And what happens when we take the graph of this function and subtract 1 from the y coordinate? If we're subtracting 1, isn't that the same as adding a -1? We're taking the graph of this function and we're adding -1, which means that we're going to shift this graph -1 units in the positive direction, or we're going to shift this graph 1 unit in the negative direction. And that's exactly how we get the graph of f of x equals absolute value of x minus 1. We're going to take this graph and move everything down 1 unit. So here's -1. The point 0, 0 gets moved down 1 unit. In other words, we subtract 1 from the y coordinate, and we get the point 0, -1. Then we take these 2 points. We shift this point down 1 unit. The y coordinate is 1 here. It's going to be 0 here. We take this point, move it down 1 unit. X is still 1, but y is going to be 0. And voila. That we've got the graph of the new function. Now, before we do anything involving horizontal alterations of the graph of a function, let's combine all 3 of these features in 1 or 2 examples. Next example. We have -3x squared plus 2. And to figure out how to graph this thing, we're going to refer back to the basic function in our repertoire that most closely resembles this, and that's going to be x squared. Now, what should we do first? Well, let's see. We have 3 times x and -1 times 3x. I'm sorry. We have 3 times x squared and negative 1 times 3x squared plus 2. Remember, we always multiply and divide first and then add or subtract last, unless parentheses tell us to do otherwise. So the addition here, we save that for last. And what I'm going to do is just draw some intermediate functions, adding features until I get to this thing. The first graph that I want to draw is f of x equals 3x squared. Here's our reference function. Wow, that's a 2. And it looked like a boomerang that hit a rock. How do we get this graph from this graph? We just take the original and stretch it out by a factor of 3. The y coordinate here is 1. That's going to be 3 on our new graph. Okay. So we just graphed 3x squared. Now we'll add one more feature. F of x equals negative 3x squared. And when we take this graph and multiply by negative 1, what does that do to this graph? Doesn't it take this graph and flip it around the x-axis? So everything that's above the x-axis is now going to be below. Oh, we're looking good. And then finally, I take this graph and I do the last thing that I have to do, add 2. When I add 2 to the graph of this function, isn't that going to take this function and move the whole thing up vertically 2 units? I think it will. So this point at 0, 0 is going to get moved up to 0, 2. And this point at negative 1, negative 3 is going to get moved up 2 units from negative 3 to negative 1. This point also is going to get moved up vertically 2 units from negative 3 to negative 1. Oh, that was as easy as stealing candy from a baby, not that we would ever do that. But, you know what? In a short period of time, we've learned how to graph some pretty complicated functions. There's a trick to doing all of this. I think we're about ready for horizontal alterations, but let me, what the heck, let's do one more example, okay? Okay, f of x equals 2x cubed plus 2. How do we graph that? The first thing we do, for the sake of reference, is just draw a graph of one of the basic functions in our repertoire that most closely resembles this. And I think that's going to be f of x equals x cubed. So let's draw that. Here's the graph that we use for reference. Now, what's the next thing that we're going to do to it? Remember, we multiply and divide before we add and subtract. So let's look at the graph of f of x equals 2x cubed. And what is this 2 do to the graph of x cubed? It stretches it out vertically. The y-coordinate of this point is 1. The y-coordinate of the corresponding graph on this, the corresponding point on this graph is going to be 2 times 1. The y-coordinate of this point is -1. So the y-coordinate on the corresponding graph, the y-coordinate of the corresponding point on this graph is going to be -1, -2. We just multiply this y-coordinate by -2. Beautiful. And now we're ready for our final product. Add 2. f of x equals 2x cubed plus 2. How does adding 2 to the y value affect the graph of this function? Doesn't it just send everything up 2 units vertically? So I'll tell you what. I'm going to draw points. The graph isn't going to change shape. It's just going to move vertically. This point I'm going to take and I'm going to add 2 units to it. I just added 2 to the y-coordinate of this point, so this is going to be x equals 0, y equal 2. Okay. So I know where my y-axis is. This point, I'm going to move up 2 units. The y-coordinate here is -2. That's going to become 0. 1, 0. Oh, you know what that means? Y is 0. This is the x-axis. And this point, I'm going to move up 2 units. The y-coordinate was 2, but I'm moving the point up 2 units, so now it's going to be 4. And there's our new graph. This graph intersects the x-axis at x equal, excuse me please, x equal -1. It intersects the y-axis at y equal 2. And notice the shape of this graph is the same as the shape of the original graph. All we did was we stretched it vertically by 2 units, and then we added 2 to jack this whole graph up 2 units. Okay, now at long last we're going to look at horizontal alterations. I'm back, and we're ready with some horizontal alterations. And I will say that the horizontal alterations are not as intuitive as the verticals. The horizontal alterations do pretty much exactly the opposite of what we'd expect them to do. The first alteration has to do with stretching and compression horizontally. And the way that a function can be stretched or compressed horizontally is by taking x, not f of x, but x, and multiplying it by some constant c. And we'll just deal with positive constants here. So this is not c times f of x. This is f evaluated at c times x. And let's see what this does to the graph of y equals f of x. Notice that the graph goes through the point 1, 1. And here it looks like the graph goes through the point where y is 1, but what is x? We'll have to wait and see. Again, this graph goes through the point y equal 1. In the original graph, the x coordinates are -1 and +1. And I think I put these in prematurely here. The y coordinates I like, I'm going to keep them. But what x coordinate causes f of cx to be 1? We might guess -c and +c, and it would be a good guess, but it's not quite right. It turns out, well, let's see. I know how we can reason on this. Let's go back to the graph of the function that we use for reference. And what do we have to plug into f of x to make the y coordinate equal to 1? Don't we plug 1 into f of x to make y equal 1? Or don't we plug -1 into f of x to make y equal 1? So y is going to be 1 when the inside of this function is equal to plus or minus 1. What would c have to be to make c times x equal, what would x have to be in order for c times x to be equal to 1? Wouldn't x have to be 1 over c? Or if cx is -1, y is 1. So if x is -1 over c, c times x is -1. And now all of a sudden, we have the coordinates of this graph, but they're not what we'd expect them to be. We'd think, wait a minute, we're multiplying x by c. That should stretch this graph out horizontally by a factor of c. And you know what? It does just the opposite. If we multiply by c, it compresses the graph. And I guess we'd say by a factor of 1 over c. So this is not nearly as intuitive as the vertical alterations. Let's look at some examples where we're not using arbitrary constants like c, but we're using real flesh and blood constants like 3, 5, -2, Let's look at some examples and see how this affects the graphs horizontally. Graph the function f of x equals 3x quantity squared. Is our reference function. We use the basic function in our repertoire, f of x equals x squared. And we refer to this graph to draw the graph of the related function, f of x equals 3x squared. The graph's going to have the same basic shape, but the scale, the horizontal scale, is going to be different. Our graph is going to look like this. And I put this down prematurely. I don't think this is really going to be the x-coordinate of that point. Oh my goodness. I did something else really silly. It's 3x in parentheses squared. Now let's look at this point. The y-coordinate is 1. On our graph for reference, in order for our y-coordinate to be 1, the x-coordinate has to be 1. In other words, when we take x and we square it, we get 1. So if we want the y-coordinate to be 1, whatever it is that we're squaring has to be 1. That's the key. To get a y-coordinate of 1 on the graph, whatever it is that we're squaring, -1 or +1, has to be 1 when we square it. So for this point, we want the x-coordinate, or we want what appears in the graph here to be +1. What would x have to be in order for the inside here to be equal to 1? 1/3, right? 3 times 1/3 gives us 1. So the x-coordinate is 1/3. And over here, on the original graph, the y-coordinate is -1. And right here, the y-coordinate is 1. Please forgive me. And on the original graph, the corresponding point has an x-coordinate of -1. So we want whatever goes in here, whatever it is that's being squared, we want that to be -1. What would we multiply 3 by to get -1? It would have to be -1/3, right? So what have we done by taking what it is that we're squaring and multiplying the inside by 3? That essentially compresses the graph horizontally. I guess we'd say by a factor of 1/3. Now that we've seen how this works, let's do 1 or 2 more examples. New example, graph f of x equals square root of 2x. The graph that's in our repertoire of basic functions that we use for reference is f of x equals square root of x. Here's the graph. And the graph of f of x equals 2x is going to have the same shape, but the horizontal scale is going to be different. I want to know what x coordinate goes in here. And what we've been seeing is that if we take the inside of the function and multiply by a number, that compresses the graph by a factor of 1 over that number. So I'm guessing that since the x coordinate here is 1 on the original graph, the x coordinate on our variation is going to be 1 over 2 times 1. In other words, we've compressed it by a factor of 1/2. I'm guessing that's how it works. Now I've got to check myself. I'm going to take this number, this x value, put it in the function, and see if I get that y value. So I'll put 1/2 in for x. I have 2 times 1/2 is 1. The square root of 1 is 1. It works. Okay. I think I'm starting to get this. Let's do another one. Here's another example. F of x equals absolute value of 3x. And to graph this, we look at the basic function in our repertoire of basic functions that most closely resembles this. And that's the graph of f of x equals absolute value of x. Now I expect the graph of this function to look a lot like the graph of absolute value of x. The only thing that I expect to change is the horizontal scale. And I'm starting to wise up now, and I realize that this isn't going to stretch the graph horizontally. This is going to compress the graph horizontally by a factor of 1/3. That's what I'm thinking. So I'll graph f of x equals absolute value of 3x. I'm going to use this as my model. Horizontally, I don't expect the graph of the function to change. So I'll take the liberty of putting 1 and 0 here. I don't know what the x-coordinates of these points are, but I do know that putting a 3 here inside the function compresses the graph by a factor of 3. So if the x-coordinate of the corresponding part in the original graph is 1, I expect the x-coordinate of this point to be 1/3, 1 over that number. And if the x-coordinate of the corresponding point in the graph of the reference function is -1, I expect the x-coordinate of the corresponding point in this graph to be -1 over that number. Now let's see if I've done it right. Let's see if I've done it right. If I should be able to take this x-coordinate, put it in for x, and I should be able to get that y-coordinate. Let's see if that happens. I take -1/3 and put it in for x. So I have 3 times -1/3 is -1. And the absolute value of -1 is 1. Looks good. Let's try it with this x value and see if I get that y value. I put 1/3 in for x. So I have 3 times 1/3 is 1. And the absolute value of 1 is 1. Okay. I got it. I got it. So I think I'm good with horizontal stretching and compressing. You know what? All of the examples that we've done so far, we've compressed the graph. Let's look at a case where it actually does stretch horizontally. F of x equals 1/2 x quantity cubed. To graph this, we refer to the basic function in our repertoire of basic functions that most closely resembles this. And that's f of x equals x cubed. Here's what the graph looks like. Now let's use this as reference to graph f of x equals 1/2 x quantity cubed. The shape of the graph should be pretty much the same. The horizontal scale is going to be different because of that one thing. So I'm going to draw the graph out. Whoops, can't do that. I don't know what the x values are going to be yet. Okay, that's what the graph looks like. But I don't know the x-coordinate of this point. I don't know the x-coordinate of that point. What I do know is that this graph is stretched or compressed by a factor of 1 over whatever this thing is. One over this thing, whatever it is, and that's 2. So apparently, I take the x coordinates in my reference function and multiply them by 2. The x coordinate of this point is 1. So the x coordinate in the corresponding point over here should be 2 times 1. The x coordinate of this point in the original graph, or the reference graph, is -1. So the x coordinate of the corresponding point in this graph should be 2 times -1, or -2. Now, let's see if this actually works. I should be able to take the x coordinate of this point, plug it in here for x, and get the y coordinate of this point. Let's see if that works. I take 2, I put it in for x, so I have 1/2 times 2, which is 1. And then I take that, cube it. 1 cubed is 1. Oh, it works. Let's try it for this point just to make double sure. I should be able to take the x coordinate of this point, plug it in for x, and get the y coordinate of this point. Let's see if I do. I take -2, I plug it in for x, so I have 1/2 times -2 is -1. And then I take -1 and I cube it, and I still get -1. Oh my goodness, this works. Ah, excellent. Well, enough of compressions and stretching for right now. We have one more thing to look at, and that's horizontal shifts. This is another horizontal modification that doesn't do exactly what we'd expect it to do. Y equals f of x plus c. Suppose we have the graph y equals f of x. The graph of y equals f of x plus c shifts, oh, that's a big one. Got to underline that. Shifts the graph of y equals f of x c units to the left. Our intuition would say, well, plus, positive direction, c units to the right. Doesn't happen. Y equals f of x plus c shifts the graph c units to the left. And so we might be wondering, okay, well, what happens if we had y equals f of x minus c? There it is. Y equals f of x minus c shifts the graph of y equals f of x c units to the right. It sort of does exactly the opposite of what we'd expect it to do. Let's look at some examples. f of x equals absolute value of x plus 3. To graph this, I refer to the basic function in my repertoire of functions that most closely resembles this, and that's going to be f of x equals absolute value of x. Here's what the graph of f of x equals absolute value of x looks like. And let me add one more detail for good measure. We know what the original function looks like, and we know what this does. Horizontal shift left 3 units. I think this is the point that I'm going to focus in on. It's at the origin, and I'm going to move it 3 units to the left. 1, 2, 3. Everything else is the same. So let's see. We have the vertex right here. We take this point, 1, 1, move it 3 units to the left. So the y-coordinate stays the same. But the x-coordinate, we start at x equal 1 and we go 3 units to the left. That's going to be x equal negative 2. And this point, the y-coordinate's going to stay the same. But the x-coordinate, negative 1, is going to get moved 3 points to the left. So we start at negative 1 and go 3 units to the left. That's negative 4. And there's our new graph. Graph f of x equals x minus 1 cubed. To do that, we go to the basic function in our repertoire of basic functions that most closely resembles this. F of x equals x cubed closely resembles f of x equals x minus 1 quantity cubed. So we look at this graph for reference. And the shape of the graph should be the same. It's just going to be, what happens here? This is the thing that does whatever to the original graph. And we say horizontal shift. Let's see, x minus 1, that's going to shift positive direction. It's going to shift right 1 unit. So here's the x and y axis. Here's x equal 1. Here's x equal 2. Here's x equal negative 1. And this is a vertical alteration also, so it should change. I'm sorry. This is a horizontal alteration only. So it shouldn't change the vertical aspects of the graph. This point is going to be moved 1 unit to the right. Zero, zero, the origin becomes 1, 0. And this point, 1, 1, gets moved 1 unit to the right. That means we're adding 1 to the x coordinate. Yeah, okay. This point gets moved 1 unit to the right, so it's going to be on the y-axis at y equal -1. Then there's our graph. We just picked this son of a gun up and moved it 1 unit to the right, horizontally. Next example, we're going to combine both horizontal alterations. And then we're going to throw horizontals and verticals together. Holy moly, look at this thing. F of x equals quantity 1/2 quantity x minus 1, whole thing squared. I don't want to do all of this at once. I want to do it step by step, just like we did the verticals. It's easier for me. It's probably going to be easier for you. Now, this thing is going to stretch or compress the graph horizontally. Subtracting 1 is going to shift the graph horizontally. Which one do we do first? Remember we said multiply and divide first, add and subtract second? But now there's something new. Whatever's inside the parentheses, we do those first, right? Parentheses first, then multiply or divide, then add or subtract. So whatever's in the parentheses, we do that first. Oh, we know what this baby does. Horizontal shift. And this is negative, so it's going to go to the right. 1 unit. I can do that. This point is going to go 1 unit to the right. This point is going to go 1 unit to the right. It's going to be right on the y-axis. This point is going to go 1 unit to the right. Then y is going to be 1. And we go 1 unit to the right, so we're going to go starting at x equal 1, 1 unit to the right, so x is going to be 2. Cool. We have f of x equals x minus 1 quantity squared. Now we have to incorporate multiplying by 1/2. of x equals 1/2 x minus 1 quantity squared. Holy moly. It's going to shrink. No, let's see. Stretch horizontally by a factor of 1 over whatever this is. It's going to stretch everything by a factor of 2. Okay? The x coordinate, so in other words, every x coordinate is going to be multiplied by a factor of 2. The x coordinate here is 0, so that point stays right where it is. We're stretching everything by a factor of 2. So this x coordinate is going to be multiplied by 2. The y coordinate stays the same. This x coordinate is going to be multiplied by a factor of 2. I think I'm right. I better check first. I'll take the x coordinates of each of these points, plug them in, and see if I get the y coordinate. X equals 0. I take x equals 0 and I plug it in here. Oops, I don't like what I have. Hold on a minute. You know what? This isn't right. Let me tell you what I did and what I should have done instead. I made a big deal about doing what's in the parentheses first. And you know what? Inside this outer set of parentheses, we take everything on the inside and square it. So on the inside, we have to perform this operation first. We have to do what's on the inside of this set of parentheses first before we can square. Did I do that here? No. I squared x minus 1, and then I decided I was going to multiply by 1/2. I made a big deal about doing what's inside the parentheses first, and that's not what I did here. So let me do it the way that I should have done it. Let me do it the way that I said I was supposed to do it. Okay, this is what I'm really graphing. I distribute the 1/2 first. I do what's inside this outer set of parentheses first. I get 1/2 x minus 1/2. And then I'm squaring this mess. So first I graphed f of x equals x squared. Now what I want to do is graph f of x equals 1/2 x quantity squared. And let's see, what is that going to look like? This is horizontal stretching, isn't it? going to stretch by a factor of 1 over this thing. So we're going to stretch everything by 2. Horizontally. The x-coordinate here is 0, so if I multiply it by 2, I still get 0. The x-coordinate here is 1, so if I multiply it by 2, I'm going to get 2. The x-coordinate here is negative 1. If I multiply it by 2, I get negative 2. Okay. So I just stretched the graph horizontally. Instead of these points being at x equal negative 1 and x equal positive 1, they're at x equal negative 2 and x equal positive 2. Now we'll do the next step.